Hi. So last video I talked about how hybridization allowed us to get sp3 to bind 4 things to carbon, or sp2 to bind 3 things to carbon. And now let's look at another way, another orientation, another hybridization, the sp hybridization. So if we were to hybridize sp, we would take one s orbital and one p orbital to make these new sp orbitals. And because we are putting 2 orbitals in, we get 2 orbitals out. And because an sp orbital has one s and one p, there is 50% s and 50% p. So energetically, they're right in the middle. And so if we're looking at the shape of s and p, because we're only using one p, and let's say we're using p in this along this purple line axis, the new sp orbitals would also be in this purple line axis. But we also have some leftover orbitals, 2 p orbitals, and they both remain orthogonal to the original sp orbitals. So the s and p, the orientation is 180 degrees, so things that are bound in sp orientation are 180 degrees away from each other. But the remaining p orbitals are 90 degrees, and we'll see what that looks like in the following slide. So let's look at a few molecules that have sp character in them. The first that we're going to look at is called acetylene. So we can draw it like this, as simply 3 lines. Sometimes we'll draw it this way so you can recognize that there are indeed protons, or hydrogen atoms rather, at the ends of these molecules. And the chemical formula of this is simply C2H2. So first, let's look at the carbons. So you have 2 carbon atoms, and they both have sp hybridized orbital. And again, these sp hybridized orbitals are facing each other. One thing you might notice about the sp orbitals I've drawn is they kind of look a little bit lumpy. That is, they look a little bit more bulbous than the previous orbitals I've drawn, and that's because there's more s character in them. So they're going to look more like an s orbital, which is more like a sphere. So they're a little bit closer to the nucleus. They're tighter in. We'll look at the ramifications of that later as well. So we can also now look at the extra p orbitals involved. So one of them, I've just drawn it in as this blue one, is in the plane of the board. So currently all these are in the same plane. The next orbital now is coming out of the plane of the board. That's sometimes hard to visualize, but you can make a model of this and really help you to see it. And so again, one of the other lines that's drawn up here, I've highlighted it now in yellow, and I've just used yellow to show the phasing of this particular orbital, and these are coming out of the plane of the board at you. What are those hydrogen atoms? Well, the carbon has an sp orbital going in both directions, as we saw on the previous page. So each carbon has 2 sp orbitals. One I've drawn in black, and the other now I've drawn in red. And this red sp orbital is interacting with this hydrogen atom to make a bond. I'll point out that these, when you have double bonds or pi orbitals, it's not that the electron density is simply like a little flagpole here, but in reality, when we share the electron density in an orbital, we're kind of smearing the electron density across both atoms. And so, and that happens for both the ones that are in plane and the ones that are out of plane, the ones that are coming out of the board at us. You can almost think about this as a fan coming toward you and a fan coming this way. Another way of visualizing that is to look directly down the bond. So that's what that eye is supposed to represent. We're looking directly down this carbon, this hydrogen to carbon to carbon to hydrogen bond. And so if we were to do that, the only thing we would really actually see is this first atom that we see, the hydrogen atom, and we would see sticking up is this p orbital drawn in blue, and 90 degrees from it, we would see this yellow highlighted p orbital as well. Let's look at a couple other molecules that also have sp hybridized carbon in it. So acetonitrile is a molecule and a solvent that you might interact with in lab. And so the line structure of acetonitrile is simply like this. If we were to figure out how many hydrogen atoms and to draw out the carbons in this, we would draw that there's a CH3, so there's a methyl group at the end of acetonitrile. There's this central carbon that is sometimes hard to see with sp because there's no angle to the bond that's being drawn. But it's you can tell there's a carbon there because you've gone from a single line to a triple line, to a line with three lines. And then finally, of course, the nitrogen atom is there as well. And we, as is our convention, we draw in the nitrogen atom. So the methyl carbon is sp3 because it's bound to 4 different things. The central carbon is sp, it's only bound to 2 things, and it's 180 degrees from those 2 things. And the nitrogen atom is also sp, and it is bound to 3 things and it is bound to 2 things, where one of those things is a carbon and the other is actually not bound, but it has a lone pair of electrons, and that lone pair of electrons is in the plane of all this carbon, nitrogen, and lone pair of electrons are all in the same plane. It's like a little arrow. Another molecule to look at is carbon dioxide. And so carbon dioxide looks a little different than the other ones. We often think of sp hybridized atoms as having a triple bond, but this central carbon doesn't have a triple bond, but it has a double bond on both sides. So that central carbon is only bound to 2 different things. So it is sp. In one direction, you can think about it having the p orbital maybe highlighted in blue, as we've seen before. And in the other orientation, we have a p orbital that is 90 degrees from that p orbital on the left. This creates kind of an interesting twist to the way the orbitals work in this molecule. I highly recommend making a model. We'll do this in class as well, so you have a chance to really visualize what this molecule looks like. It's a very interesting molecule, even though it's very simple in terms of chemical formula and highly abundant on Earth. Well, thank you for your time. I look forward to seeing you next video.